In this video, we're going to talk about the definite integral. And so, something that we mentioned the last two videos is we saw limits of the form the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. We saw this show up for two different things. We saw this coming as the area under the curve f of x, and also this was the distance traveled by a particle with velocity f of x. And so we saw this show up two different places, and so we're going to give this a name in a sense, and that will be the idea of the definite integral. So let's remember the setup. So if f is a function defined on a less than or equal to x less than or equal to b, we divide the interval a to b into n sub-intervals of equal width delta x, which is b minus a divided by n. We let x0 be a, x1 is equal to a plus delta x, and so on up to xn is equal to b. The endpoints of our subintervals and we let x sub 1 star, x2 star, up to xn star be any sample points in the subinterval xi to xi plus xi minus 1 to xi. So xi star is in between xi minus 1 and xi. Then we define the definite integral of f from a to b as we write this as the integral from a to b. That's what the elongated s means. It just means the integral from a to b of f of x dx is defined to be the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star delta x. And so this is what we call a definite integral. And it's really just a shorthand for these limits of sums that we saw before. Okay? And now this assumes that the limit exists. The limit exists and has the same value for any choices of sample points. And we're going to see in a minute that that is not actually that strong of a condition for most functions we'll care about. But we do have to actually assume that the limit exists in this definition. Otherwise, we're defining something that doesn't exist, and that's a little weird. And then one other piece of terminology is if the integral from a to b of f of x dx exists, we say f is integrable on the interval a to b. And so something's integrable on an interval if its definite integral exists. So let's talk about a little bit of notation when it comes to integrals. And so we have this elongated ace from a to b, f of x dx. The f of x is what we call the integrand. A and b are called the bounds of integration. And the dx tells us what variable to integrate with respect to. Now, hopefully, this notation does remind you a lot of the sum that we were doing before. And so we were originally doing the limit as n goes to infinity, the sum from I equals 1 to n of f of x sub I delta x. And so kind of a way to group this is the limit of the sum becomes the integral from a to b. The f of x of x sub I just becomes f of x, and the delta x becomes dx. And so the notation is very similar to the notation we had before. It's just kind of a shorter way of writing it all down. Now, one thing to be aware of, this is a common mistake that gets made. So when we write the integral from a to b of f of x dx, this is a number. Okay, it's not a function. This is just going to be some number. It'll be the area, if f of x is a positive function, this will be the area under the curve from a to b. So like if we look at a graph of some function from a to b, then this area here is literally just the integral from a to b of f of x dx. Okay, so it's just a shorthand for the type of thing we were doing before. But things get a little more complicated if you take a function that's not always positive. And so if f takes on both positive and negative values, then the integral from a to b of f of x dx is the net area from a to b. Now, all this means area above the x-axis is counted as positive, and the area below the x-axis is counted as negative. And we actually see this from the rectangles. So we haven't really looked at an example like this before because it's a little bit more complicated, but if we have some situation like this, and we're going from A to B, if we were to draw rectangles, like we were doing last time, just using right endpoints, one thing you'll note here is that when I get to drawing over here, all of a sudden I am now drawing below the x-axis, which might not seem concerning at first until you realize how we were finding the areas of these rectangles before. So remember the way that we found the rectangles where we were looking at f of x sub I times delta x. Well, for all of these values down here, f of x sub I is going to be a negative number. And so f of x sub I times delta x will be treated as negative if we're below the x-axis and positive if we're above the x-axis. And the integral takes that into account. So the integral counts everything up here as positive and everything below the x-axis it'll count as negative. And so when it does the whole integral, what it does is it's going to take the area above the x-axis minus the area below the x-axis. And that's what the integral actually is computing. That's what the definite integral finds for us. If you want to figure out like the total area and treat everything below as positive, you need to use absolute values of something in the function to kind of flip it up. And in the future we will talk about how to deal with things like that. Now, one thing to be aware of is integrals can be kind of hard to compute, and so we usually approximate them. And so we approximate integrals using what we call Riemann sums. Now, a Riemann sum is a fancy way to describe something that we've already talked about. So Riemann sum is just any sum from I equals 1 to n of f of x sub I star times delta x. So in other words, they're the sums that we were looking at before without the limit. Okay, we just pick some n, and we're going to approximate the definite integral by picking some fixed n and just computing things like that. Okay, so it is something we have done before. There's nothing particularly special about it, it's just now we're giving a name to those sums. And so let's look at an example of computing something using Riemann sums. So we want to approximate the integral from 0 to 3 of x cubed minus 6x dx with 6 subintervals using right endpoints. Okay, so we want to approximate this integral using rectangles rather than actually finding the actual value. We'll compute the actual value of this later in this video. So now what we want to do is we first want to convert this into a Riemann sum, and we're going to compute it into like the limit of a Riemann sum, and then we're just going to forget the limit part and restrict ourselves to 6. And so remember that the general relationship is the integral from a to b of f of x dx is equal to the limit. So n goes to infinity of the sum from I equals 1 to n of f of x sub I star times delta x. And so we need to compute each of these pieces in this limit of the sum to get our Riemann sum. Well, the f of x is really easy. It's the thing we were taking the integral of. And so it's going to be x cubed minus 6x. It's the integrand. Now delta x, we've talked about this before. That's b minus a over n. Well, b is in this case 3, because we're taking the integral from 0 to 3. So it's 3 minus 0 divided by n. Now we're going to do it in general first, and then I'm going to restrict it in the case of 6. So I am going to use n and find this limit first, and then we'll just drop the limit and plug 6 in for n. And now x sub I star, we were told to use right endpoints. And as you might remember, the formula for the right endpoints is a plus I delta x. Okay, so that's the formula for right endpoints. We mentioned that in the last video. A in this case is 0. I is obviously I, and then we just found delta x is 3 over n. So we're going to have 3i over n. Okay, so x sub I is 3i over n. And so what we're actually looking at then is the integral from 0 to 3 of x cubed minus 6x dx equals the limit. So n goes to infinity of the sum from I equals 1 to n of x, xi is 3i n, so we've got 3i over n cubed minus 6 times 3i over n. And then we multiply this by delta x, which is 3n. And so this then is our summation that we're doing, but we were told a specific n. We're approximating it. We don't want the whole limit. So we're going to forget the limit part, and we're just going to use 6. And so what we're looking at then is our approximation is just the sum from I equals 1 to 6, n is 6 now, of 3i over n, but n is 6, cubed minus 6 times 3i over n, which is 6, times 3 over 6. Okay, so that is the sum that we are then computing. And so just plugging in values here, this is going to then be equal to 1/2. I'm just going to pull the 1/2 out. So it's 1/2 times the value of the function. So we're going to have I over, I'm going to actually range over the I. So we're going to have 3 over 6 cubed minus 6 times 3 over 6 plus 6 over 6 cubed minus 6 times 6 over 6, and so on. I'm not going to write all of them down. The last one is going to be 18 over 6 cubed minus 6 times 18 over 6. So that's just writing down each of the terms in the sum. I'm kind of grouping things together like we normally would. I'm just plugging in the values for I. And this becomes 1/2 times negative 2.875 minus 5 minus 5.625 minus 4 plus 0.625 plus 9, which is negative 3.9375. And so this gives us an approximation for the integral. Now notice that this value is negative. And that's just because if you actually look at the graph, this is a very rough sketch of the graph. The graph looks like the following. And so when we actually draw these rectangles, what's happening here is we find that there is just more area underneath the curve than above the curve. Okay, and I drew 7 rectangles instead of 6. Like I said, I did not do a very accurate job drawing it. I'll just fix it like this. Okay, so we have something kind of like this happening, where we just have more area below than above. And so since there's more area below than above, what ended up happening then is we got a negative value, which is just totally fine for an integral. There's nothing wrong with that. Now, when it comes to integrals and approximating them, there is one rule that tends to be a little bit more accurate if you really want to approximate. And so that is what is called the midpoint rule. And all the midpoint rule is this says use the midpoint of each interval as your sample point. Okay, so this is just one way of approximating integrals. It tends to be more accurate than using left endpoints or right endpoints. You'll sometimes see it written down as the integral from a to b of f of x dx. It's approximately equal to the sum from I equals 1 to n of f of x sub I bar delta x, where delta x equals b minus a over n, and x sub I bar is equal to x sub I minus 1 plus x sub I divided by 2. So x sub I bar is literally just the midpoint of the interval xi minus 1 to xi. You're just picking the thing right in the middle. And so let's look at an example of doing the midpoint rule. Okay, so we want to use the midpoint rule with n equals 5 to approximate the integral from 1 to 2 of 1 over x dx. Okay, so our interval is 1 to 2, and so that means then if we actually compute delta x is 2 minus 1 over 5 in this case, so we're going to have 1/5. So delta x is 1/5, and so the intervals that we're looking at are going to be 1 to 1.2, 1.2 to 1.4, 1.4 to 1.6, 1.6 to 1.8, and 1.8 to 2. Just to 2. And now for the midpoints, we're just taking the thing in the middle of each of these. The middle of 1 to 1.2 is 1.1, then 1.3, 1.5, 1.7, 1.9. And so those are our values that we're then approximating it with. Okay, and so what we then have is the integral from 1 to 2 of 1 over x dx is approximately equal to delta x times f of 1.1 plus f of 1.3 plus f of 1.5 plus f of 1.7 plus f of 1.9, which this equals, remember delta x is 1/5, so we have 1/5 times 1 divided by 1.1 plus 1 divided by 1.3 plus 1 divided by 1.5 plus 1 divided by 1.7 plus 1 divided by 1.9, which is approximately equal to 0.691908. And so this gives us, using the midpoint rule, an approximation. Okay, so it's just another way of finding an approximation for the value of the integral. Because as we will see in a minute, computing an integral actually is kind of hard to do in general. And we're going to do that by actually computing the integral for the expression that we looked at a second ago. Okay. So now to kind of point out why computing an integral is somewhat hard, we're going to actually compute the integral from 0 to 3 of x cubed minus 6x. Okay, so we approximated this earlier. This was the one we used the right endpoints on. I used midpoints here just because it's with a different example, just because it's easier to plug things in there. But now we want to find the actual value for this. And we want to see it takes quite a bit more effort than just plugging things in. Okay, so we want to first convert this to a Riemann sum, We did this, limit of a Riemann sum. We did this once before above, so I'm going to do it a little bit faster here. Okay, so remember that it's equal to the limit of the sum from I equals 1 to n of f of x sub I delta x. So f of x is going to be x cubed minus 6x. Our delta x is b minus a over n, which is 3 minus 0 divided by n. And x sub I, we can always use right endpoints when we're actually evaluating a definite integral. It doesn't matter which endpoint, what you pick as your sample points. So you can always use right endpoints. I think if you always use the same thing, you tend to have an easier time remembering it. So we're just going to take the right endpoints here, which is a plus I delta x, which in this case is going to be 0 plus I times 3 over n. So we get 3i over n. And so our integral from 0 to 3 of x cubed minus 6x is equal to the limit, so n goes to infinity, of the sum from I equals 1 to n of x cubed minus 6x. Sorry, need to plug things in. It's equal to 3i over n cubed minus 6 times 3i over n times 3 over n. Okay, so I'm actually plugging in the stuff we just found. Okay, now we want to compute this limit. Now we have done limits like this in the past, so we're going to just use techniques that we have used before to compute the limit. So this is the limit. This n goes to infinity. Now I'm going to pull 3 over n out in front, so we have 3 over n times the sum from I equals 1 to n of, we need to do 3i over n cubed, so we're going to have 27i cubed over n cubed minus 18i over n. So I just multiplied things through. Now we can factor stuff out. So we have the limit as n goes to infinity of 3 over n times, in this case we have the sum from I equals 1 to n of 27i cubed over n cubed minus the sum from I equals 1 to n of 18i over n. So I just broke it up into two sums. That's a property of summations. If you don't recall all the properties of summations, it might be helpful to go back to the sigma notation video to recall those. And this is limit as n goes to infinity. 3 over n times, I'm going to pull stuff out. So I have 27 over n cubed times the sum from I equals 1 to n of I cubed minus 18 over n times the sum from I equals 1 to n of I. So I'm just factoring things out. Next, I'm going to multiply the 3 over n in just to make things look a little bit nicer. So this is the limit. So n goes to infinity of 81 over n to the 4th times the sum from I equals 1 to n of I cubed minus 54 over n squared times the sum from I equals 1 to n of I. And now we're going to use our formulas that we have for summations. Again, you can find these in the sigma notation video. I'm just going to write them down here. So the sum from I equals 1 to n of I cubed is n times n plus 1 over 2 squared. The sum from I equals 1 to n of I is n times n plus 1 over 2. And so we're going to plug those in to have the limit as n goes to infinity of 81 over n to the 4th times n times n plus 1 over 2 all squared minus 54 over n squared times n plus 1 over 2. And now we need to simplify this expression. So we have the limit as n goes to infinity. I'm going to multiply things out. And so we have 81 over 4, I'm just pulling factors out, and n squared times n plus 1 squared divided by n to the 4th. So I've grouped the constants together, grouped the n's together, minus, we're going to have 27n times n plus 1 divided by n squared. That just comes from 54 divided by 2 is 27. We can cancel 2 of the n's out on the first one and 1 of the n's out on the second one. And so this again gives us the limit. So n goes to infinity of 81 over 4 times, I'm going to multiply the top out, so I have n squared plus 2n plus 1 divided by n squared minus, we're going to have 27n plus 27 divided by n. So we have the limit as n goes to infinity of 81 over 4 times 1 plus 2 over n plus 1 over n squared minus 27 minus 27 over n. So I distributed the negative through there. And now from here, we just want to actually take the limit of each piece. That's why I wrote it down the way I did. So 2 over n will go to 0 as n goes to infinity. 1 over n squared goes to 0, and 27 over n goes to 0. And so we're left with 81 over 4 times 1 minus 27. And if you compute this, this ends up being negative 27 over 4, which is negative 6.75. And so we were able then to compute, just as a reminder, what we found is the integral from 0 to, it was 3, I think. Let me look, yeah. 0 to 3 of x cubed minus 6x dx is equal to negative 27 over 4. So that's what we just did. But notice how much work it took. Okay, we started the problem right there, and that's how many steps it took. So because of this length of process, it is pretty common to use Riemann sums. That's why I went through the whole how to approximate them first. This can be kind of a lengthy and involved process, and it does require you to remember your sigma notation formulas and things like that. Okay, so we're now going to do one more example of converting a sum into an integral. Okay, so just trying to be able to be fluent in going back and forth between the two. Okay, so we've done examples of converting integrals into sums. Now we're going to go the other way. So we want to express the limit as n goes to infinity of the sum from I equals 1 to n of xi cubed plus xi sine of xi times pi over n as an integral on the interval 0 to pi. Now an important thing to note here is if we don't give you the interval that you want the integral on, you can get more than one answer. Okay, so this is not like a only one unique answer if we don't give you the interval. All you'd be doing is like shifting the graph, basically. But if we give you the interval, then you're fixed to a single answer. Okay, and so what we want to do is we want to find the integral from 0 to pi of some function f of x dx. And so the key here is to figure out basically what is f of x. Okay, well we know this is the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star times the dx. Times delta x, sorry. And so we kind of pattern match is what we do. And so first, we can figure out what delta x is. Delta x is b minus a over n. In this case, it's pi minus 0 over n, which is pi over n. And so our pi over n is right there. And so this whole piece here in our summation, that's f of x sub I. I'm going to write x sub I because x sub I is what I actually have written there. And so now, what have I plugged x sub I into? Well, it looks like I've plugged x sub I into the function f of x equals x cubed plus x sine of x. Notice that's what I've plugged x sub I into. And so because of that, that must be our f of x. And so our integral is then just the integral from 0 to pi of f of x, which is x cubed plus x sine of x dx. Okay, and so that allowed us to convert our summation into an integral. Now we could have written this in a bit more complicated of a way. Instead of writing down xi cubed plus xi sine of xi, we could have written this as the expression pi over n cubed plus pi over n sine of pi over n. So this is actually using what x sub I equals. Remember, x sub I is a plus I delta x, which in this case, if you actually plug things in, just ends up being, I forgot my eyes. It ends up being pi I over n. And so you'd have pi I, I pi over n cubed plus I pi over n sine of I pi over n. So these two things are equivalent. You could see it written in either way, and so being fluent and going between the two is very helpful. With, again, the two key facts being delta x equals b minus a over n, and x sub I is equal to a plus I delta x. Those are kind of the two key things to use when you're converting a sum back into an integral. And really, when you're doing this, you're really just figuring out what is f of x. So now we want to talk about some properties of integrals, of definite integrals. Okay, and so the first is a theorem that is a very helpful theorem. And it says if f is continuous on the closed interval a to b, or if f has only a finite number of jump discontinuities, then f is integrable on the interval a to b. That is, the integral from a to b of f of x dx exists. Now, this is actually a very strong result. Basically, what this is telling us is if we're looking at a continuous function, this limit of the summation always works. It always exists. We actually mentioned that in the area video. When we talked about the area problem, I mentioned that as long as your function is continuous, that limit of the sum always works. This is the theorem that tells us that happens. But the interesting thing is you can have a finite number of jump discontinuities, and you're still fine. Okay, I'm not going to really justify why that's true. There's a lot of kind of advanced mathematics that goes into this result, but it's important to recognize that you do have this result. Okay, next we want to talk about some more properties. And so the next property is the following. And so it says that the integral from a to b of f of x dx equals the negative integral from b to a of f of x dx. So in other words, if you want to flip the bounds of integration, just flip which one's on top, you put a negative out in front. And the way you see this is if we actually take the first one, this is the limit, then goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x, which is the limit. So n goes to infinity of the sum from I equals 1 to n of f of x sub I, and I'm going to write x sub I star here. And then delta x, remember, is b minus a over n. Well, if I want to do from b to a instead of a to b, I just need to flip things here. I need to flip the b minus a to be a minus b. So we're going to have the limit, as n goes to infinity, of the sum from I equals 1 to n of f of x sub I star times negative a minus b over n. I just pulled a negative out to flip the order I was adding things in. To flip the order delta x was written in, I mean. And this, then, we can pull the negative all the way out in front to get the negative limit. So n goes to infinity of the sum from I equals 1 to n of f of x sub I star times a minus b over n. Well, a minus b over n is our delta x for the integral from b to a. So this is just then the negative integral from b to a of f of x dx. Okay, so it's kind of a weird trick here, but all we're basically doing is we're just saying, well, I'm just going to do everything in the other order. So you're just pulling a negative out of your delta x to flip the negative here. Okay, so that is our first property of integrals. Now I'm going to write down all of the others. I'm going to sort of justify some of them. Most of them are fairly self-explanatory, though. So we have properties of integrals. And so we're going to let f and g be integrable functions and c be a constant. Okay, so the first of these we already did. The integral from a to b of f of x dx equals the negative integral from b to a of f of x dx. We just justified that a second ago. Next one, the integral from a to b of c times dx equals c times b minus a. Now, this one is not too hard to actually prove. All you have to do is just convert this summation into this limit integral, into a summation. It's the limit. So n goes to infinity of the sum from I equals 1 to n of c times delta x, so b minus a over n. And now, remember that a summation of just a constant becomes n times that constant. So this is the limit. So n goes to infinity of n times c times b minus a over n. And look what that becomes. The n's cancel and you get c times b minus a. Okay, so this just is literally coming from direct computation. If I did that a little fast, it might be helpful for you to actually write it down yourself. You're just literally evaluating the integral, though, using the fact that the sum from I equals 1 to n of a constant is just n times that constant. Okay, our third property is the following. It's the integral from a to b of f of x plus g of x dx equals the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Now this shouldn't be too surprising. Remember, we're taking a limit of a sum. We can split up sums over addition. So that's all we're doing here, is basically just splitting up the sum over addition. Property the integral from a to b of c times f of x dx equals c times the integral from a to b of f of x dx. All we're doing here is using the fact we can pull constants out of summations and out of limits. So we're just pulling the constant multiplying by f of x out of everything. And so that's why that result is true. Next, we have the integral from a to b of f of x minus g of x dx is equal to the integral from a to b of f of x dx minus the integral from a to b of g of x dx. Same argument as for addition, you can just split up over subtraction, because you can do that in limits and summations. Now the last one we want to talk about is the following. The integral from a to b of f of x dx equals the integral from a to c of f of x dx plus the integral from c to b of f of x dx if a is less than or equal to c, less than or equal to b. Now this one might seem a little confusing at first, but basically we're just saying I'm just going to split up my summation in pieces. And so what we originally had, I'm going to draw a picture to describe this. What we originally had is we had some situation like this. It doesn't have to be an area under a curve, but the idea transfers. So we originally were looking at this whole area. That's the integral from a to b of f of x. Well, all we did is we said, okay, there's some value c in here. What we're going to do is we're going to find the area from a to c, this piece, and then add on to it the piece from c to b. So we're basically just saying I'm going to stop somewhere in the middle and do it as a sum of two pieces instead of as just one whole thing. Now, this might seem like a weird thing to do, but sometimes it's helpful to split it up just for computing purposes. Sometimes it's easier if you don't go all the way. Okay. And so now we're going to use some of these properties for examples. So we're going to do some examples of these. We're going to start with property f, the one I just talked about. And so we want to suppose the integral from 0 to 10 of f of x dx is equal to 17, and the integral from 0 to 8 of f of x dx equals 12. We want to find the integral from 8 to 10 of f of x dx. And so by the property we just mentioned, the integral from 0 to 8 of f of x dx plus the integral from 8 to 10 of f of x dx is equal to the integral from 0 to 10 of f of x dx. But we can plug in some of these values. The integral from 0 to 10 is 17, and the integral from 0 to 8 is 12. And so plugging those things in, we have 12 plus the integral from 8 to 10 of f of x dx is equal to 17. So the integral from 8 to 10 of f of x dx is equal to 5. So it's fairly straightforward to do this. Now, it might seem a little weird to have a situation like this. What happens is that sometimes you'll have approximated these, and because of how you measured things, you might know pieces of it, but not have like the whole picture. And so what we're doing here is we're using the pieces that we can find to kind of get our missing part. Hopefully that makes sense. Now we want to talk about comparison properties of integrals. And so I'm basically just going to state these as they're fairly straightforward. So first, if you have a function f of x that's greater than or equal to 0 for all values between a and b, then the integral from a to b of f of x dx is greater than or equal to 0. Now, thinking of this as an area under a curve, this is just saying if you take a function that is always positive and find the net area under the curve, you get a positive number. Next, if f of x is greater than or equal to g of x for a less than or equal to x less than or equal to b, then the integral from a to b of f of x dx is greater than or equal to the integral from a to b of g of x dx. And the idea here is just using basically the previous one. So if f of x is always greater than or equal to g of x, then the integral from a to b of f of x minus g of x is going to equal to 0. So you have the integral from a to b of f of x dx minus the integral from a to b of g of x dx is going to equal to 0. So the integral from a to b of f of x dx is going to equal to the integral from a to b of g of x dx. So I'm just sliding over my g of x term, basically. And the third of these comparison properties is if m is less than or equal to f of x is less than or equal to capital M, for a less than or equal to x less than or equal to b, then little m times b minus a is less than or equal to the integral from a to b of f of x dx is less than or equal to capital M times b minus a. Now, this might look kind of complicated, but in reality, all we are saying here is we're just using property 2, where we're using a fixed constant little m and fixed constant capital M. And so, like, this is kind of like a g of x and an h of x, and then we're just applying property 2, using the fact we know how to take the integral of constants. We talked about that earlier. That was one of our properties. It's this property right here, property b. And so little m and capital M are both constants, so we know how to compute their integrals, and so that's literally all we are doing there. But the reason why we care about this is this gives us a way of approximating integrals, as by the extreme value theorem, we talked about that a while ago. By the extreme value theorem, a function f of x has a global max, I should say a continuous function. We are assuming it's continuous. Continuous function f has a global max and global min on the closed interval a to b. And so all we're doing there, so basically saying little m is the global min, and capital M, so little m is the global min, capital M is the global max, and then we can bound our integral pretty quickly, just finding the local min and local max. So that gives us a nice way of finding the bounds for a definite integral. And like we said before, computing definite integrals is kind of hard, so getting bounds on it is pretty nice. So let's look at an example doing this. So we want to estimate the integral from 0 to 1 of e to the minus x squared dx. Okay, so we're just going to try to get bounds on this. So the function f of x equals e to the minus x squared is decreasing on 0 to 1. This isn't too hard to see. If we take the derivative of the function, we get negative. So let's actually take the derivative. So we're going to use the chain rule. So we have e to the minus x squared times the derivative of minus x squared, which is minus 2x. So we get negative 2x e to the minus x squared. Notice that's negative from 0 to 1. Okay, so that's how we're getting it's decreasing on 0 to 1. And so that means that at 0, we're going to have the global max, and at 1, we're going to have the global min. Okay, and so capital M is going to be f of 0, which is e to the 0 squared, negative 0 squared, which is 1. And little m is going to be f of 1, which is e to the minus 1. And so using our comparison before, with e to the minus 1 times 1 minus 0 is less than or equal to the integral from 0 to 1 of e to the minus x squared dx. It's less than or equal to 1 times 1 minus 0. Or 1 over e is less than or equal to the integral from 0 to 1 of e to the minus x squared dx is less than or equal to 1, which is about 0.367 is less than or equal to the integral from 0 to 1 of e to the minus x squared dx is less than or equal to 1. And so we were able to find bounds. We've got bounds on the integral from 0 to 1 of e to the minus x squared using this comparison, which would have been kind of hard to find otherwise. And so this becomes a very useful property that we just found, as we were able to get bounds on this very hard to compute integral.